For generations, we viewed Earth as a lonely oasis, a single wet marble floating in a vast, sterile cosmic desert. This perspective is built on the assumption that liquid water requires direct warmth from a star. Under this model, a planet must sit within a narrow orbital band, close enough to avoid freezing, but far enough to stay below the boiling point. But the actual data collected from our neighboring planets tells a different story. Scientists now estimate that the rest of our solar system contains 25 to 50 times more liquid water than all of Earth's oceans combined. If we redraw our solar system map based strictly on liquid water volume, the primary centers of habitability shift away from the sun and toward the outer reaches. Finding this water requires us to look past the reach of starlight and investigate the dark, pressurized environments of the deep interior. We begin the update to our map at Mars. On the surface, the planet is a desert. The atmospheric pressure is only 0.6% of Earth's, meaning any liquid water would immediately boil away or freeze. However, ground-penetrating radar from the Mars Express orbiter detected a stable 20-kilometer-wide body of water trapped 1.5 kilometers beneath the southern polar ice cap. At this depth, temperatures are estimated at negative 68 degrees Celsius. Normally, water in this environment would be frozen solid. The water remains liquid because it is saturated with calcium and magnesium perchlorates. These salts act as a chemical antifreeze, lowering the freezing point enough to maintain a subglacial reservoir. The Martian lake demonstrates that liquid water does not require a warm climate. It only requires the right chemical composition. To find even larger volumes of water, we have to travel to the gas giants, where the sun's energy is too weak to melt ice. Jupiter's moon, Europa, is covered in a thick shell of ice, but beneath that crust lies an ocean estimated to be 100 kilometers deep. Europa alone contains 3 billion cubic meters of liquid, twice the volume of all Earth's oceans. Further out at Saturn, the moon Enceladus actively vents geysers of salty water and organic molecules into space, providing direct evidence of a global ocean hidden beneath its surface. Even the tiny moon Mimans, once thought to be a solid block of ice, shows orbital anomalies that point to a stealth ocean deep within its interior. The heat source for these oceans is tidal heating. As these moons orbit massive planets like Jupiter or Saturn, gravitational pull stretches and compresses them. This constant physical distortion creates internal friction, generating enough heat to melt the surrounding ice from the inside out. Even further out, dwarf planets like Pluto and Ceres may stay liquid through the radioactive decay of their rocky cores, which keeps their deep interiors warm for billions of years. In these outer reaches, gravitational friction and internal decay replace starlight as the primary drivers of a liquid environment. When we apply these observations to the rest of the Milky Way, the scale of potential habitability expands. Since gas giants and icy moons are common products of planetary formation, NASA's 2020 mathematical models suggest that exoplanets with internal oceans are likely a standard feature across the galaxy. We are already seeing the evidence through spectroscopy. Using the mirrors of the James Webb Space Telescope, researchers have identified atmospheric water vapor on exoplanets like WASP-96b, over 1,000 light-years away. This abundance of water forces a change in how we define a habitable world. We now know that life could potentially exist in total darkness, powered by the same gravitational friction we see in our own outer solar system. The completed map of our own neighborhood shows a system defined by these hidden reservoirs. Our solar system was never a desert. It is part of a vast cosmic archipelago, with the most significant volumes of water waiting beneath the ice.